of the experiment in yellow. This is a real picture of the structure which they used. So you see, this is a sapphire, sapphire substrate. You have here a launcher of microwave. At this point, you have a little gap, and this is a piece of the resonator, which is here. The resonator is snake-like laid out because the frequency of few gigahertz corresponds to, let's say, 10 gigahertz is 3 centimeters. Okay? If you have silicon, epsilon of silicon is about 11.5. And then if you have a transmission line on the surface, then the effective speed of light is decreased by square root of 11.5 plus 1. Half spaces vacuum, half spaces silicon. So this is a factor of roughly 3.5. Slow down. So on chip, you will have the wavelengths of about 1 centimeter at 10 gigahertz. And if you want to make a resonator, basically it's not enough space because you have only a few millimeters. That's why you have to make to wind this transmission line, and then you have a capacitive gap here and a capacitive gap there. And capacitive gap then is very such that you can change the capacitance of this gap. So if you do it very, very sharp here, the capacitance is very small, and then you basically see too little signal. So you have to play it with coupling strengths of the cavity in order to make the observation comfortable. And in this point here, in the center of the cavity, you see this very first charge qubit, which is coupled to the cavity. These are two tunnel junctions. This is a Cooper pair box, and this is the bulk electrode. So everything here is connected to the ground. And basically, with this experiment, they've really seen very beautiful behavior. So first, they see the resonance frequency of the resonator. This is transmission from here to here, microwave transmission. And then when they brought the qubit in resonance with the cavity, then the cavity frequency shifts, and that's the signature of the interaction between the qubit and the cavity. So you see here the whole schematics is very simple. So you apply here through some attenuators from microwave source and DC break, you apply the frequency to this resonator. It's characterized by this effective lumped model with inductance and capacitance. This is the resonator together with its capacitances. This is capacitively coupled qubit, Cooper pair box. Then the signal which is transmitted goes to the circulator, which is the device with 3 ports, and every port is coupled to its neighbor on the right side, and not coupled to the neighbor on the left side. If you put one of the ports of the circulator to 50 ohm, then this device becomes an isolator. Circulator становится вентилем, and this isolator basically transmits the signal from left to right, but doesn't transmit signal from right to left. It's so-called non-reciprocal device. It's needed to avoid the back action of the amplifier on the cavity here. So the signals in this direction they propagate, in this direction they don't propagate. This is a cold amplifier, high electromobility transistor silicon amplifier, which typically has a noise temperature of a few Kelvin. And then at room temperature, you have a mixer where you mix the frequency which you receive after amplifier with the reference frequency which you apply. And then you have the amplitude and the phase. You have the intermediate frequency output here. Typically, you have not just one output, but two, which are two quadratures rotated by 90 degrees phase. We'll talk about this a little later. And then if your qubit is detuned from the cavity, you see the transmission through the cavity is a bit. So if you exactly the resonance frequency of the cavity, it's about 6.04 gigahertz, then you just see a peak of transmission. However, if you bring the qubit in resonance, you have very strong interaction between the qubit and the cavity. And then, depending what you want, if you want to excite the qubit and then transfer the excitation to the cavity, that's why you go in this situation here. Here, the excitation will be quickly swapped between the qubit and the cavity, and then you have the two states with detuned cavity from the resonance. Now, the model is described The system is described by this Hamiltonian. It's again the equivalent circuit. I borrowed this slide from Andreas in one of his lectures. So basically, this is again the photons in the cavity. This is the qubit charge term. This is the qubit Josephson term. This is the two-level system, basically. And this is the frequency which you apply, which is basically a classical field of photons in the applied by external microwave. This beta is proportional to the amplitude of the signal in the cavity. So basically, it's the physical amplitude then multiplied by the effective capacitance, which is given by this formula using this C terms above. Then, if you consider now this Hamiltonian and then only two lowest lying qubit states, can consider all qubit as a two-level system, then you have the quantum-ready Hamiltonian, which is written by this term. And then one can treat this, the quantum-ready model by applying the rotating wave approximation. And then you have the raising and lowering operators, which are written in this form here. So this is the expression for this operator here. And then you have four terms, exactly. But the idea of the James Hamilton's model is that one can drop this term and this term completely, because they are rotating very, very fast. In rotating wave approximation, they counter-rotate the terms, and therefore they rotate in this frame very fast. And then one keeps only slow terms, which are this term and that term. Of course, I'm not going into this model. I'm not a theory guy, so I just sort of give you a reference. And this paper by Alexander Blair appeared nearly back-to-back with a Nature paper. So this is the whole theory of this cavity QED, or circuit QED with junctions. The experiment of Nature was published in the same year, 2004. So the main idea is basically in this model to have the coupling term between the qubit and the photons in the resonator, to have this coupling term G to be much larger than the decay of the photons from the cavity because of the coupling to the environment, and also the dissipation in the cavity, which is characterized by gamma. So this is again the picture which was observed in the very first paper. So this is the cavity frequency, and in the qubit, now this is the voltage which is applied to the qubit. And it's interestingly, actually, in this setting here, they applied the voltage very simply. They applied the voltage just to this electrode. Because there is a capacitance between this electrode and that electrode, this polarized the electrons on this middle electrode, and then in turn polarized the electrons in this island here. It's a very simple experiment. You don't need any extra electrodes here to do things you want. And then when the qubit was actually moved down to the cavity, they observed here the dispersive shift of the cavity. So what happens here is when the qubit frequency becomes close to the cavity frequency, then the degeneracy because of the interaction between them is lifted, and there will be hybridized states of qubit in the cavity, which will be those two states exactly at the resonance. So if we tune the qubit frequency, now this is the picture. This is the frequency of the cavity, and this is the qubit detuning. This could be done by a gate or by something else. So in this situation, the cavity has its own frequency, it has its own resonance, and this is the qubit. So the cavity feels the qubit a little bit, but only a little bit. So this is you could use for measurements. But if you want to smooth the excitation in the cavity, what you do, you bring the qubit exactly to the resonance in the cavity. In this case, instead of single resonance, you have two resonances. One of them corresponds to this state. Qubit is in the ground state, cavity in the excited state, and this is cavity in the ground state and the qubit in the excited state. And this is the antisymmetric superposition. And this is or maybe other one. I don't remember of the two states. So there are two states, and these states live in the degeneracy of the kind of unrest cavity states, and the qubit being in the excited state. So this is the qubit in the excited state tuned to the cavity. All right, there are two effects. So if the qubit is detuned from the cavity, then the cavity knows about the qubit. and other way around. There are two parts which are interacting. Of course, also the qubit knows about the cavity. So both qubit and cavity got influenced by this interaction. And if one just takes the James Cummings Hamiltonian and then writes this only slow terms, which are important for the interaction, then one can characterize everything by the parameter delta, which is detuning between the cavity and the qubit. If the delta is equal to 0, then you're exactly in the resonance, and if it's not equal to 0, you are strongly detuned. And then one can work out the perturbation theory in the second order coupling divided by detuning. This is the dispersive regime, when the detuning is larger than the coupling strength. Coupling strength is typically, let's say, 10, 20 megahertz, and this can be, for example, gigahertz. So this is a small parameter for qubit detuned from the cavity. Then the Hamiltonian takes this form, and this is very instructive. On one hand, the photons in the resonator gets modified by the state of the qubit. So the resonance frequency of the cavity is shifting. It's not anymore the resonance frequency without interaction, but actually it's proportional. The shift is proportional to g squared divided by delta. On the other hand, the qubit frequency is also modified. And it's modified here by this factor here, which is very similar. However, it's only for the single photon excitation in the cavity. If you have more excitations in the cavity, if you have many photons in the cavity, then you have also the dispersive shift, which depends on the number of photons. And that's very beautiful, actually, toolbox to measure also non-classical states of microwaves in cavities. Again, this is the same picture in single photon manifold in the cavity. You have dispersive qubit readout. You have the frequency shift, which you could use to read out the state of the qubit. If the cavity frequency shifts, then for the qubit ground state, it will be this resonance frequency. For the qubit excited state, this will be this resonance frequency. If you measure the phase as a function of frequency of the transmitted signal, then exactly at the resonance, the phase changes by pi. And then here for the ground state of the qubit, the phase shift will be like this. And for the excited state, it will be like this. So you can use either the amplitude or the phase signal to measure the state of the cavity. If you have, for example, here in the middle, then you have large amplitude transmitted to the cavity. If the qubit changes the state, the amplitude drops down to this value. Or you could use, you could measure the phase, and then this will be the contrast of your measurement. Now, there will be, of course, the shift of the resonator and the qubit depending on the number of excitations. And this is something which is not, of course, in the single photon manifold. It's also includes also the high states in the cavity. And this is typically the picture of the shift of the qubit as a function of the cavity occupation state. This is a 0 photon in the cavity. This is 1 photon in the cavity. This is a 2 photon in the cavity. This is 3 photon in the cavity. So basically, the qubit state depends on the number of photons in the cavity. If the qubit state, if the number of photons in the cavity is here, the qubit frequency is there. However, the electromagnetic field of a photon shifts the frequency of the qubit. If you have 2 photons, the shift is larger. And 1 photon shifts the frequency of the qubit by this amount, 2 photons shift by this amount, this shifts by that amount, and so forth. And this is the calculation which comes out of the full model, including the higher cavity states. So basically, the cavity can be used to read out the qubit, which is good news because you could measure the state of a quantum system and then do something. For example, you do the quantum computing by manipulating the qubit, but you need to read out the information from the qubit. This you could do by dispersive shift of the cavity. On the other hand, the qubit is a versatile tool to measure states of the cavity. As you know, cavity is a harmonic oscillator. It has different photon occupation numbers. 0 photon, 1 quantum lowest energy state, 1 photon, 2 photons, and so forth. If you switch on microwave source is like a laser, right? So it produces a coherent light. It means that actually the distribution of the occupation of different photon number states in the cavity is Poissonian. And if you then use the qubit to interact with the cavity, then you can prepare versatile non-classical states in the cavity. For example, one can prepare Fock states. Fock states are particular states in the cavity, non-classical, where you only prepare one particular photon number. This kind of experiments have been also beautifully done with superconducting qubits, preparing Fock states up to photon number 15 or so. So it's a bit away from our field, but it's very interesting to compare also Rydberg atoms and ions with superconducting qubits. This is a very instructive, picture from the paper by David Schuster. It's again, he was at that time still in Yale. Also worked at that time with Andreas Weiler. He's now professor in Chicago. So basically, this is a detuning of the cavity from the qubit, the very same delta. And this is the coupling strengths. And they're both normalized by the maximum loss rate. So this is the loss rate which is combined by coupling the cavity to the external world, by dissipation in the qubit, and by dissipation in the cavity. And basically, with the Rydberg atoms and conventional atoms, you are somewhere down here. So you're in the limit of weak dispersive coupling. If you use superconducting qubits, then by designing the coupling strengths of the dipole of the Cooper pair box to the cavity, one can make the interaction very strong, but goes in the limit of so-called strong coupling. And in the strong coupling regime, one can actually can do it's a very powerful tool to manipulate the quantum systems. Actually, it's not so easy to describe it because all the quantum optics interaction of light with atoms has been leaning on perturbation theory, just for the reason that the dipole moment of an atom is small. However, if you take the superconducting qubit and couple strongly to the microwave cavity, the interaction is not small, and the perturbation approach breaks down. Do not use perturbation approach, a very strong coupling. Therefore, the whole story of describing a single qubit and multi-level cavity becomes really very difficult task. One requires a lot of computing power to be able to describe a two-level system coupled to harmonic oscillator of the many photon states included in the perturbation. So it's very interesting story, but it also actually is very powerful to apply to real measurements. This is a beautiful paper of Yale group where they were using a qubit detuned from the cavity in order to measure the photon occupation states in the cavity. So occupation state with a 0 photon number, 1 photon number, 2 photon numbers, and so forth. And you see here that this is the cavity resonance frequency. This is a detuning. This is the qubit frequency. And then the qubit frequency is detuned from 0 photon number state to 1 photon number state, 2 photon numbers, so different number of photons in the cavity, shifts the qubit frequency by AC star shift step by step. And then by measuring the amplitude of the peaks, one can basically make a quantum statistics of microwave light in the cavity. That's the data which they measure. This is the number of occupation number, average occupation number of photons in the cavity. This is very low number of photons in the cavity. This is about 1, about 2, about 3, about 4, and so forth. And you see that actually the occupation from 0 photon number shifts to higher photon numbers, and roughly this envelope reminds me of the Poissonian distribution for the coherent light. All right, so this is a bit away from the field of superconducting qubits, but I encourage you really to look into the review papers which I put in the archive on this disease, and I really strongly recommend you to broaden your knowledge about that, because superconducting quantum circuits is not just quantum computing. There is a lot of beautiful physics, which we only partially touch in this course. And this beautiful physics involves non-classical light, propagating photons, photon states and cavities, photon states and transmission lines. And this story actually is decorating now very often the front pages of Science and Nature and other journals. It's a very active and hot field nowadays. All right, let me start with the next stack of slides. I will rearrange them, of course, according to the presentation which we have today. Now we officially start lecture 8, but I will move part of the story in my slides. Share screen again. Okay. So in the following next hour, roughly, we talk a little bit more about KVD. We discuss also capacitive and inductive coupling. Then I'll show you a few examples of circuit QED with flux qubits, where you couple not to electric field, but to magnetic field. And then we start to the transmon qubit, which is a long story, but we'll not rush there. I will probably only begin today and then continue with you online next week. This is a generic picture of the flux qubit. And this circuit, which was made back many years ago in the group of Evgeny Ilichov, the very same Ilichov who wrote this textbook in Russian. So basically, if you have a flux qubit, you could couple it to the cavity, even to the lumped cavity, but you typically would think that you need to couple flux qubit inductively, because you control the flux qubit by one negative flux. It doesn't mean that you cannot couple the flux qubit capacity. For example, if you couple here the electric field between this point and that point, this electric field will be non-zero at high frequency because of large inductance on the other side. But the most natural approach is, of course, to couple flux qubit inductively. And instead of using full wavelength resonator or half wavelength resonator, which has antinodes of electric field at the end, people use here a quarter wavelength resonator, so a resonator which is grounded on one side. So make the finger like this. This is the ground. This is all superconducting. And if this length here is lambda by 4, quarter wavelength resonator, then here we have maximum amplitude of the electric field, and here you have maximum amplitude of magnetic field, because the current flows here up and down. And that's a picture. This is the electrode of the resonator, and this is the qubit, which was made probably like maybe 18 years ago or so. This is again a 3-junction qubit. You recognize here 2 larger junctions at this point and 1 small junction. And then you couple this to the central wire of the coplanar waveguide lambda quarter resonator. And then the current flowing there will, of course, induce oscillating magnetic field in the qubit. And when you do this, then of course you could also apply DC magnetic field flux, and then this will change the resonance frequency of transition between the ground state and excited state of this flux qubit, according to the formula to the parabola, which you should remember. It's not written here, but it's qubit frequency is proportional to square root of delta square plus epsilon square. And in this particular example, delta was about 5 gigahertz, and this axis is epsilon. So you see this hyperbola. of the qubit. And this hyperbola of the qubit depends on the flux which you apply. Frustration is basically difference from half-flux quantum. And this is the calculation. If the cavity would have the frequency of 10 gigahertz, then the qubit will cross the cavity frequency. And at the crossing point, there will be a void level crossing induced. So the cavity is then coupled to the qubit. Actually, the strong coupling limit in quantum optics is such that you can distinguish two separate peaks here. Two separate peaks is a strong coupling that you have two peaks instead of one. And then the qubit is very strongly interacting with the cavity, exactly what the frequency is measured. So this is the data measured. You see it's very similar to this green plot here, which is the result of the calculation of the eigenenergies. And this is an example, actually, of a technique which was pioneered in my group about 10 years ago, which is now being used by all companies. Unfortunately, we didn't patent it. I thought it's not very important, but the idea is basically to use the circuit QED approach and read out in circuit QED dispersive coupling to measure many qubits using a single measurement plug. So the problem, if you make a computer out of superconducting qubits, you have many qubits, you want to talk to any qubit you choose, and then the number of wires increases very rapidly. And a very simple idea, which is being used actually in cell phone technology, in satellite communication, everywhere, is the frequency division multiplex. So you have basically a channel, a wave, which propagates in this one-dimensional transmission line. This could be a signal which comes to our iPhone in free space. And then you have different qubits which are coupled to different cavities. And each cavity has its own resonance frequency. So if you propagate here a signal which is different from frequency of particular cavity, then the qubit is not influenced at all. And basically, if you want to read out a particular qubit, you can basically talk to the qubit by choosing the frequency. This is the lowest frequency, this is a bit higher frequency. And this is the data. Well, basically, this left plot shows you the transmission. Now, transmission is high in this direction and low in this direction to the right. These are different resonances here, different cavities. Basically, each cavity is this kind of finger which is coupled to the transmission line. And if you, for example, apply the frequency about 10.25 gigahertz, you couple exactly to this qubit. If you apply only 9.3 gigahertz, you couple to this qubit. And then by driving the whole chip here with external second tone, this is the so-called two-tone measurements to read out qubits, one can make pictures of spectra of the qubits. And this is done in the following way. Suppose you choose the qubit you want to measure. Then you apply a frequency to the transmission line, which is close to the resonance frequency of the cavity which is coupled to the qubit. And then you apply also the second tone, which drives the transition in the qubit. And if the qubit is being excited from the ground state to the post-excited state, it shifts the resonance frequency of that particular cavity. So the cavity frequency is shifted, and then you basically observe the change in the transmission. So instead of measuring with a single microwave tone, you use two tones because one is needed to make spectroscopy of the qubit, to apply some arbitrary frequency which will excite transition in the qubit, and the second tone is needed for the readout. And this is the contrast, which is the change of the readout tone, amplitude, and phase as a function of magnetic flux for different qubits here. And you see here that these qubits have different, there were here 7 different qubits. They have different frequencies. This, for example, has the lowest frequency of 2 gigahertz. This is 5 gigahertz, it's 5.8. This is 6.2, 4.4, 6.4, and 2.0. Actually, it's very difficult to make identical qubits. In particular, it's very, very difficult to make identical flux qubits because the frequency is exponentially sensitive to the difference between the area of a small junction and the large junction, with respect to alpha. And this ratio is, of course, done by lithography. So you see this is a larger junctions, this is a smaller junction. So very small variation of the grain size of deposited aluminum will make the junction area slightly different. But nevertheless, in this very first experiment, it was possible to observe the spread of frequencies, which was in the range for the, if not count the very left and very right qubit, it was in the range of about 20%. Actually, the group of John Martinez at the University of California in Santa Barbara did a similar experiment half a year later, and then basically it was picked up by all team players. So the group of John Martinez was hired by Google in 2014, and basically now this dispersive readout is being used in a variety of architectures to measure superconducting quantum circuits, chip superconducting processes. Of course, you need to make sure that the signal you apply here is not having too large amplitude not to saturate the amplifier, which you have, of course, on some here on the right. And if you want to measure many qubits, you need to apply larger power, and therefore you risk a saturation of the amplifier. So practical rule is that typically people use between 5 and 10 qubits coupled to a single measurement line, but this greatly reduces the overhead of making extra wires for superconducting circuits. Any questions?
Можете объяснить, пожалуйста, на рисунке D, там есть два волновода, между ними подается волна, а что за точка?
Ну, это мусор. Мусор какой-то, не знаю, литографический какой-то мусор остался, но ни на что не влияет. То есть здесь вот имеется волновод прямо 4, и это его открытый конец. А заземленный конец находится там, где находится кубик здесь. Вот. И фактически электрическое поле микроволновки распространяется по этой линии, оно связано с полем резонатора, а сам резонатор, соответственно, если пройти по этому резонатору наверх, нарисовано вот здесь находится кубик, который вот здесь.
А желтая это система охлаждения?
Нет, желтая это хитрость. Дело в том, что эти кубиты, они очень чувствуют флуктуации магнитного потока. И когда такая сверхпрямая пленка охлаждается в криостате, то всегда существуют какие-то паразитные магнитные поля, поле Земли или поле железа, любые разъемы коаксиальные, они все немножко магнитные, потому что там есть нефть. Вот. И эти магнитные поля, они приводят к тому, что возникают в этой пленке, вот в этой области, возникают абрикосовские вихри. То есть это вихри квантомагнитного потока, которые пронизывают пленку. И дальше, если возникает высокочастотный ток, этот ток начинает двигать эти вихри, возникает диссипация. И могут перепрыгиваться в области, делают магнитный шум. Чтобы этого избежать, делают специальные дырки, которые служат фактически ловушками для вихрей. Если вихрь пришел и сел в эту дырку, он уже не двигается, он нам не страшен. Окей.
Допинговать вихрь, который ловушки нельзя никак. Допинговать вихрь, который ловушка уже нельзя никак.
Но очень трудно его вытащить, потому что нужно закупить энергию, которая потребуется для того, чтобы курс снизился к войне. Можно подать параметр. И это стоит дополнительной энергии. Если он сел туда в дырку, уже его вытащить очень трудно. Тут очень большие ток. This picture is an illustration for a actually very interesting field, which is being developing in Yale for about the last maybe 8 years. This field was a separate lecture course. And this is an alternative approach of doing quantum computation using not superconducting, not qubits, two-level systems, but rather using cavities. Linear cavities with multiple with many energy levels. And these cavities actually can be favorable for two reasons. One is that the quality factor of this cavity, the broadness quality factor, can be huge. It can be in the range of billion, not million, but billion, 10 to 9, 10 to 8, 10 to 9. So microwave photons will live in these cavities for a very long time, much longer than they will live in planet cavities. Second reason is that this particular architecture of coupling the cavities to qubits and also cavities themselves makes it possible to implement a very interesting alternative approach to quantum error correction. So one can encode the states of the cavity in superposition states of equal photon numbers, but shifted by phase pattern. In this case, the effective field of the cavity, due to this superposition, is virtually zero. And the coupling to the external wall there for this particular superposition state is actually negligible. But this is a really very interesting direction. People interestingly use something similar to this, not two-dimensional, but no three-dimensional. Imagine a cylinder which you drill in a piece of superconductor, and then in the middle of the cylinder you leave a little stuff, like a little rod which sticks out from the bottom of the cavity. So this is all whole, and this is superconductor, and outside also is superconductor, and the top part is open. And interestingly, if you irradiate microwaves here, microwaves reflect from the bottom of this hole and go back, you will see a resonance. This resonance corresponds to frequency which is corresponding to quarter wavelengths of the length of this rod, of this star. The quality factor of this resonance, as I mentioned, is really huge. It's 10 to 8, even 10 to 9 numbers were reported. And basically, the states of photons in this cavity are they live for a very, very long time. They live for not now few hundreds of microseconds, but rather for tens and hundreds of milliseconds. And then one can use superconducting qubits to manipulate states in this cavity and actually form a particular non-classical photon states, which can be then used for the error correction. There is a whole architecture there of making the trans-1 qubit to couple the quantum memory with the quantum readout and so forth. This is a really very interesting direction. And it all actually is existing thanks to the development of this cavity QED. So there are not so many groups in the world. I know only of the group in Yale, where this paper can be looked up. There might be also a recent review from Shokov and others. And also groups in China pursuing this field. Well, still the practical algorithms have not been demonstrated. So there was a demonstration of the error correction recently, and there are some protocols which are quite promising going towards quantum error correction. So I just mentioned that this cavity QED also has sort of value for its own, and also has some interesting physics in it. All right. With that, we will have another half an hour, and we start talking about рабочая лошадка квантовых процессоров на сверхпроводниках, about transmons. This is the working horse of all superconducting quantum processors. There are many pictures. This picture is maybe like already, I don't know, 3-4 years old. You see here fragments of superconducting quantum processors from IBM. It's one of the very first, back maybe 6 years ago. From Rigetti, from IBM, more recent, and this is from Delft, a collaboration with Intel. But Delft stopped this work. I think they didn't stand competition with IBM and Google. And this is the processor of Google, which also is based on transmons. We'll talk about this a little later when we discuss also more advanced topics. So what is a transmon? You know already about the phase two. You know this washboard potential, and I told you that to have new energy levels, you need to tune the washboard potential and make this enharmonic potential strong enharmonic at current close to the triple current of the junction. Suppose now you make the junction which is small. And in this case, you have naturally, if you make the capacitance of the junction smaller and smaller, which means the effective mass of the virtual particle decreases and decreases, then you have only few energy levels in this cosine potential, even if you don't tilt. So you have a phase cube, which has the potential of cosine. You don't apply any current, so just flat cosine. And then you adjust the capacitor such that you have only 8 to 10 levels confined to each potential. This is one way of looking at transmode heat. And this is, in this case, the coordinate for the cosine is the phase. Now, as we talk about the quantum system, you can present the system in the phase basis or the charge basis. You get, in the charge basis, you get the dependence on phase, and the phase basis, you get the dependence on the charge. So you can diagnose the Hamiltonian in different frame. And it's also instructive to talk about transmode from the charge, from perspective of the charge cube. This picture we have seen already today. This is the charge cube, which has the Josephson energy of the order of the charge cube. And in this case, we have a large gap. And these parabolas, which we discussed before, they are split now into the lowest energy state and the society state. There's also here. And these states, they oscillate as a function of charge, which you apply to the superconducting. And I told you already that one of the problems of the charge field, which actually prevent charge fields to be used for practical devices, is that small fluctuations of charge here, which has always existed in non-electric circuits, which origin is still being debated. There are many different reasons to expect charge noise, and probably not a single reason at all, but many mechanisms which contribute to that. It doesn't make life easier. There is all this charge noise, and therefore there will be all these fluctuations in this horizontal axis, and therefore the energy level separation will fluctuate in the continuous time where there is a very low, even in the sweet spot is very cheap. You don't understand. However, let's think, if we fix now the Josephson energy, we don't touch the Josephson energy. So we make the coupling point fixed, but we increase the charging energy. How we can do it? We can simply take very small Josephson junction and put some additional capacitance in parallel. We put the capacitance 5 times larger than the capacitance of the junction, then the charging energy is reduced by a factor of 5, and the ratio of Josephson energy to the charging energy becomes 5 times larger than before. In this case, the increase of the capacitance, if we look at the Hamiltonian, this is the following. This dependence of the energy level or its energy bands on the charge is called charge dispersion. So about this device, you can tell that the charge dispersion is very large because energy levels strongly depend on charge. Here, you'll basically have much smaller charge dispersion because we increase this energy here. And this applies also to the lowest energy state, to the first excited state, and the second excited state, and so forth. If you increase even further, you go to a factor of 10, this level becomes almost flat, and this level becomes nearly flat. And if you go to 50, on this point, you cannot even see anything. It's actually now depends on the energy levels on charge on the atom or largely induced capacity. You can think of these energy levels. If we diagonalize this Hamiltonian in different bases, these are just energy levels in the cosine potential, which we discussed already this week. Just the distance is getting larger here. And the difference between the ground state and the first excited state in energy is slightly larger than the difference between the first excited and the second excited state. The reason is that we are in the phase coordinate, we are in cosine potential, so cosine is not parabola, it's only parabola close to the bottom. And if you have only few energy levels in this potential, then this harmonicity will be already quite essential. So basically, you get the sweet spot, basically no charge dispersion or almost no charge dispersion everywhere, but you pay the price. You pay the price that you're getting much smaller and harmonicity. And harmonicity means that here the energy level separation between the difference between condition 0, 1 and 1, 2 was very large. You see, this is small frequency, this large frequency. Here, this difference is a bit less. And here, the difference is actually existing, but it's quite small. It's only a few percent. So harmonizing decreases. Now, the name transmon is really strange to me. There is always competition in the scientific world, and the transmon obviously is a kind of simplified version of the phase two, which was that time developed by the Martinez at the University of California in Santa Barbara. And when Yale group came up with a similar idea, they had to invent a different name. So they invented a name which is next to impossible to disabbreviate. It's a transmission line shunt plasma oscillation tube. Now everybody knows this is a transmon. It's an abbreviation of something they invented. Of course, they came to this picture having this kind of philosophy, which is different from the philosophy of the case cubic. But physics is the same. Basically, you are getting slightly unharmonic levels in the potential, which is simply given by the cosine of physics. So transmon is now named like that, and people don't think anymore about it. How to make the transmon? I told you that we need to increase by a factor of 50, or maybe 100, their capacitance. And this needs to be done in a technology which is compatible with the way the junctions are. Junctions are made by shadow operation, so we make two polymeric layers of resist. We remove the bottom layer of resist by irradiating from high energy electrons in electron microscope in lithography machine. And then we have suspended mask, which we use to evaporate from two different angles. And the capacitance which we want to make has to be compatible with this technology. And naturally, this can be done by using the so-called interdigital capacitor. It's basically a finger type capacitor, which doesn't have any barrier. So you don't make capacitance by one field, by another field, which is a longer process, which creates extra defects in the qubit. So one has to make it very simple. По-русски это называется штыревой конденсат. In English, it's interdigital capacitor. Now, when Yale group came up with this idea, they wrote this paper, which is about 40 pages long, which is this paper that is about everything you want to know about transmon, start everything, all the Hamiltonians, all the noise sources and so forth. So basically, this is a charge qubit with increased capacitance, which can be used as a slightly unharmonic system. And it's very easily manipulated, of course, by external fields. So you don't really need much to do. You can couple it electrically to resonators. You can read them out by using the frequency division multiplexing and manipulate by microwaves. Now here there are a few formulas which are quite practical, which I may want to comment. So it turns out actually in this paper, it's all shown that one can solve the eigenenergies exactly. And by diagonalizing this Hamiltonian, one has to use Mathew function approach, and the exact formula for the energy levels is given by this expression. So these are the собственное значение функции Матье, и это специальная функция, которая их сортирует, которая специальным образом подобрана. The bottom line of this calculation is that the energy of the energy level with number m is described by this formula here, where the mean value corresponds to quarter of the charge. It's somewhere here in the middle, somewhere here, right? In the center. And then you get this cosine, which is an approximation, of course, but it's cosine containing the gate charge. So basically it tells that according to this exact solution, you can get approximate solution for the energy levels, which will describe the lowest band as the cosine. And also if you improve the perturbation limit by increasing this ratio, then also the high energy state becomes the cosine, and yet the high energy state becomes almost the cosine. And then the coefficients in front of the cosine, this is the amplitude of this corresponding energy level, is actually described by this expression, which is valid for the ratio EJ over EC, much larger than unity. So it's in the limit of it's very small capacitive energy. Quite nice. And then one can also calculate here the eigenstates in energy. And here, this is the very same expression. But now we are interested into this formula here, where we have the energy band energy to the energy level separation between 0 and 1. And here you basically have the dash line, which is the prediction of this formula, and the solid line, which is the result of exact diagonalization of the Hamiltonian. And one can see that going to a large ratio of Josephson energy to the charging energy, this perturbation approach actually is working very, very nicely. Of course, it deviates strongly for small ratio, but this is where you don't expect this approach to work. Next comment, the unharmonicity parameter. So I told you that the one is strictly unharmonic structure, so the energy level separation 0, 1 is only slightly larger than energy level separation 1 and 2. And this actually is a problem because it limits the speed of manipulation by using external microwave. So we apply very large amplitude of microwave to have the rapid frequency comparable with the difference between the frequencies 0, 1, and 1, 2. Unavoidably, we address the first level with the rapid frequencies, and we occupy also high states. So hard driving to have high rapid frequencies makes it impossible to avoid occupation of high states. And this is the picture of calculation of the energy level separation between energy level M and ground state to the charging energy. So this is obviously the ground state. This is the first excited state. This is the second excited state, the third excited state. And you see that there is slight difference here. So this is about 12 gigahertz, and this is about 23 gigahertz, and this is about 30 something. And one can write now in the same limit also the expression for the energy state M is given by this formula, where M comes into this game here. And then there is a correction here which contains also the square in M number. And basically, interestingly, it's very, very beautiful that the unharmonicity parameter, which is alpha, is nothing else as in relative units as the charging energy divided by the energy level separation between 0 and 1. So basically, if you take a transform, I think I have probably also in the second slide. No, I'm not sure. I have a lot of slides here, but let me tell it when it comes next, I will just mention it again. So basically, if you take now the Josephson energy, and this energy is factor 50 larger than the charging energy, then unharmonicity, which means the difference between 0, 1 and 1, 2 transition, is nothing else as the charging energy. So if you take now the charging energy being 50 times smaller than Josephson energy, it means that you have unharmonicity for the ratio of 50, you have an harmonicity of about 2%. 2%, this is, sounds too little. On the other hand, we operate here at frequency roughly 5 gigahertz, and 2% is as large as 50 times 2, so it's 100 megahertz. It's not bad. So one can actually make the rapid pulses in the time scale of a few tens of nanoseconds, and this will be already fast enough. On the other hand, it will be still not too fast to occupy the high states. All right. This is an instructive picture of one of my former students, Andrew Schneider, where he actually calculated the perturbative calculation with exact formulas. And again, here we have transitions between 0 and 1. This is 1, 2, transition to 3, 3, 4, 5. And solid line is the exact calculation, while the dashed line, dotted line is the perturbation approach. This is a detailed discussion of the harmonicity. Basically, harmonicity is measured in absolute units as a difference in energies between 1, 2, and 0, 1. Now, in this notation, harmonicity for transmode is negative, which means that the higher transition between the higher levels is smaller in frequency than transition between the lower levels. But it's convenient to introduce the relative harmonicity, right? And the relative harmonicity is just alpha divided by energy level separation between 0 and 1. And then, okay, taking this is the consideration which I verbally told you already, discussed in the previous slide. So how quickly you could manipulate the qubit. If you want to have this typical frequency between 0 and 1 transition and pulse duration about 10 nanoseconds, then you come up with a requirement for the minimum harmonicity given by this formula. And then the choice of the energy levels, of course, is dictated by reducing the charge dispersion in order to avoid the charge noise. So basically, the relative harmonicity which you arrive at will be in the range between 0.2 and 0.5, 0.02 to 0.05. So again, this. So basically, by compromising the harmonicity against the speed of manipulation, which largely depend, of course, on the coherence time of the transmodes, you can choose the optimal range. And initial transmodes, which sort of evolve from charge qubits, they have the coherence of the range of first maybe few fraction of microseconds, but then slowly they were improving, first in the range of microseconds, then were improving in the range of tens of microseconds. And presently, transmodes, which are well designed, have coherence times of the order of 100 microseconds. What should tell the coherence times of transmodes is limited by material defects. That's something we'll discuss in a separate lecture. On the other hand, if you take Google, they work with tunable transmodes. So the transmodes are squids, and therefore the main source of noise for them, or additional source of noise for them, is magnetic noise. And typically, those transmodes have coherence in the range of 30 to 40 microseconds. IBM decided to work on different architecture. Their transmodes are single junctions, so they're not tunable. So they have fixed frequency, and then the gates which they apply to transmodes, we'll talk about to them, are very different from all gates. And nevertheless, choosing the non-tunable transmodes makes it possible to avoid magnetic noise, and therefore their transmodes typically will have coherence in the range of almost 100 microseconds. So winning on one side, one lose the other side, and the whole story of superconducting qubits was the story of compromises and difficult decisions. When technology is being developed, like in semiconductor physics, you can imagine what was happening in the world in the 1960s. People invented transistors, and they realized that bipolar transistors dissipate a lot of power on chip. If you want to make large processors, you have to go away from bipolar transistors. And then people came up with field effect transistors. And those were very different devices, but of course consuming much lower power than bipolar. And then taking a decision which branching point. And in this branching, some technology will win, the other technology will die. But something which is developed in this technology which will die may eventually give a new branch, which will develop by itself. So it's a very beautiful story, actually, which we observed in the last 15 years about the competition of different types of superconducting qubits. And I was asked in the break, what is my favorite type of superconducting qubits? I can tell you it's not transmode. But I'm more physicist and less industrialist investing in that. All right. Any questions to that? Okay, let me move on, showing the some signatures of the transform. So I told you that transmon is weakly enharmonic, and now you see the picture of the energy levels of transmons and also the wave functions of the stationary states in the phase coordinate. So it's diagonalized in the charge basis. It's in the phase coordinate, and the cosine potential is parabolic, but its first correction actually is this one, and it's the power 4 correction. So the energy level separation between 0 and 1 will be slightly larger than 1, 2, and that one will be slightly larger than 2, 3, and so forth. And this is already beautiful data taken by my former PhD student, Johann Braunmüller, graduated actually about 5 years ago, and worked for a while at MIT. So he actually took the data on a single transmon, applying large microwave power to the transmon. And here you see the frequency on horizontal axis, and this is the driving field power in dBm. dBm is language of microwave engineers, is power in logarithmic scale reference to 1 milliwatt. 1 milliwatt is 0 dBm. This is the correspondence. You know, decibel, but if you see M, it's absolute scale, it's reference to 1 milliwatt. And of course, this power is a reference to the room temperature source. And then the color here is the dispersive shift of a resonator, which is coupled to the qubit. Now, you already know that if the resonator shifts the frequency, then basically it means that the qubit is being excited from the ground state to the excited state. However, if you drive continuously the qubit, then the qubit is coherently evolving between ground state and excited state, so it spends 50% of time in the excited state, 50% of time in the ground state. And basically, if you increase the power, you see that dispersive shift increases. Now, initially, you excite transition between 0 and 1. This is great transition, but the start of this picture is actually already at some power which is larger than the fundamental transition. So you start seeing the fundamental transition maybe at minus 30, and here we increase to minus 20, minus 10 dBm. And then if you increase power more and more, you start seeing here this very sharp dips. And then again, at even larger power, again, at even larger power. And what you observe is basically multi-photon transitions. So these transitions are multi-photon. They are not allowed in a small signal limit, but if you drive the system hard, of course, you also have high order processes. And then basically you can describe the two-photon transition from 0 to 1 as the transition through some virtual level, which is exactly in between, at the frequency 1/2 of the 0-2 transition. And this is this peak here. Now, the three-photon transition to the third state is actually this transition, and this blue arrows, they shows four-photon transition to this state there. Of course, also you see some other transitions there. You can think about what they are. We have some idea, and actually some of them you know very well. But if you have an idea, come to me and tell. Just exercise your intuition. It's a practical device, and this is simply a calculation of the Lindblad equations, the model describing the quantum system, driven quantum system anticipation. All right. Now, transmon performance is amazingly good. So it really is a very good qubit, and these are the data from I think the second paper published by Yale group already a year later after they came up with the idea. So the Rabi oscillations have very good visibility. You see these are really long Rabi oscillations with a frequency of the order of 50 megahertz. This is the T1 decay, basically applying half a period of Rabi oscillations. You excite to the excited state, and then you see by shifting the readout, you observe the decay of this population. It's in the range of a few microseconds. And this is the dephasing, the Ramsey decay, which is characterizing the T2 time. So it's actually immediately was seen as a beautiful qubit. You don't need to bias it as a phase qubit with a particular current, worrying about the current fluctuations in the current line. You only need basically you only need to the circuit for the readout, which is the microwave circuit, which is of course blocking a lot of low frequency noise components. This is a practical question. Of course, in the transmon, you always have the sensitivity to external flux if you make a squid. For example, all Google transmons, they're all tunable transmons, as I told you. And in this case, it comes also into question how to optimize the design of transmon in order to have not only one sweet spot, but more than one sweet spot. And the hack here is basically to make two junctions of the squid a little different from each other. So if you make one junction a little bit bigger, the other one a little smaller, and this is for a particular case when the difference between them is about 40%, then the modulation curve of the critical current versus magnetic flux is such that it doesn't go to zero at half flux quantum, as it does for symmetric squid, but goes to some minimum value and then saturates there. Minimum value saturates there. And then it actually, this critical current is given by this formula. Here you have this tangents instead of the cosine only. You have an additional term there. And basically, with this asymmetric squid, one can have not only one sweet spot, but also sweet spot here, sweet spot there. Of course, by taking this decision, we need to make sure that the spread of parameters between different transmons on chip is smaller than the range you choose. Because if you need to tune the transmon's full range, then to make the frequencies, for example, equal, then of course you will not be able to do this with the asymmetric transmon. But it's always, of course, not the case. So typically one chooses here the range about 30 to 40%, and then can have nearly all qubits tunable if desired with the same frequency on the same chip. All right, this is again the comparison of a symmetric transmon and asymmetric transmon, but now showing also, in addition to the ground state transition 0-1, which is blue line here and blue line there, shows also transition between 1 and 2, and you see it actually has a sort of different signature for the symmetric transmon and for the asymmetric one. For the asymmetric one, it always remains below the fundamental transition here. And you could read more in this paper, which I also put in the archive. That's actually a very detailed, very instructive paper written by MIT group, which is called Quantum Engineer Guide to Superconducting Qubits. It contains also all the knowledge of quantum mechanics you may need. So if you want to refresh some of that in your memory, just go there and read the introduction. There's a lot of stuff there. So transmons are now being used for building scalable superconducting quantum processors. And this is the prototype which was invented in the group of John Martinez in Google. This paper was published a year before they all went to Google. And this was still the work of the group in Santa Barbara. So instead of making the transmon with the sticks, which is the version of the Yale group, they realized that, of course, they have to go away from the phase qubit, which I described to you before. And not to repeat the words of competitor, they decided to call their device XMON. So the inventing names is a fashion in this field. And the reason of calling it XMON was because they decided to make the shape of the electrode of the superconducting qubit, of transmon qubit, to be cross. So this X or cross is the central electrode of the superconducting qubit. And then here, so all this line here is a capacitive gap. You see this is a capacitive gap. So basically you have metallic cross surrounded by the ground electrode of a superconductor. And then, and this only part of this cross, here we have this kind of central wire, or one of the cross parts is coming down here. And then in this area, you have electron beam lithography making the qubit. And this qubit consists of two Josephson junctions, which are connected to the ground here. And this is a squid, which changes the frequency, changes the Josephson energy of this transmon. So basically, the transmon is sitting, this junction is sitting between this electrode and the ground. Now, this line is the so-called flux line. Comes from below, and it's called also Z control. Z control means that it controls the Josephson energy of the transmon. And the reason of calling it Z, because if you prepare the superposition state on the Bloch sphere, and then you change the frequency of the fundamental transition, keeping the frequency of the excitation the same, then this variation of the frequency of the fundamental transition will effectively rotate the state on the Bloch sphere around Z axis. So this is the Z gain if you modify the Josephson energy. In contrast, if you want to rotate between 0 and 1, then of course you rotate either around x-axis or around y-axis, depending on the phase of the microwave relative to the initial phase. And this is done by having another port here where you have the microwave control. So this will be the Z rotation on the Bloch sphere. This will be X rotation and Y rotation, depending on the phase around the Bloch sphere. Then you have the upper port here, which has a capacitive coupling to this resonator, which is nicely identical to the work not done by them, but borrowed by them. Without referencing our work, but they did in the end, after the referee told them that this is wrong. So this is their readout line, which sees this resonator at this particular frequency. And this resonator basically talks to this qubit. If this qubit changes the state from ground state to the excited state, the resonance frequency of this resonator shifts. And then you have yet another port, this port, which goes to some other part of the chip. And this one can be either quantum bus, which you use to couple other qubits via cavity, or can be simply capacitive coupling to some other superconducting qubit. So basically, this is a scalable design which contains both all three Z, Y, and X controls, contains the readout, and contains the coupling to other qubits. And these qubits, which were initially proposed to be used for scaling the circuits up, were actually they are chosen as working courses for all the quantum processors we know these days. These are the numbers about T1, which was quite good, about 40, 30 microseconds on this particular chip. And this is the number of T2, which was slightly less, but you could improve this by applying the refocusing pulse in the middle. So this is the echo T2, and this is the precision decay measured from razor fringes. First experiment they've done was the chain of superconducting qubits coupled capacitively, which is a realization of the Bose-Hubbard model. And there are beautiful experiments done on this here in the electrostatic. Even nowadays, they have the similar system with 8 qubits in the fridge, and they use it as a quantum simulator. So it's very powerful, very, very robust and useful quantum simulating circuit. Now, with the very same types of qubits, Google went up to build their scalable processor, and this is the work which they first started with 72 qubits, and that was never worked. And they had to go back, and they lost 2 years on that, and redesign everything. And after they have designed it properly, they called it Sycamore processor. Sycamore is sycamore is a kind of pine tree which grows in California, and it has the fruit, the shishka, which has a similar type of geometry. That's why they call it sycamore. Anyway, they've done this work. 54 transfers. One of them didn't work, but that didn't really matter for them. So they were able to demonstrate with this processor, actually quantum supremacy, which we'll talk about a bit later. And I don't have a slide here. No, I don't have a slide here. So basically, coupled via couplers, and the coupling is between nearest neighbors. One can sort of separate this processor in one half and then take the other half and then one can simulate a classical computer, roughly 27 qubits on one half. But then simulating 53 qubits on classical computer, really doing the full simulation of the large interface is simply impossible to do even on the supercomputer in a reasonable time. Therefore, it was this experiment was called demonstration of quantum advantage or quantum supremacy. This is where the IBM is roughly now. They announced last year the 127, I think, have now announcement of the larger processor. Now, they don't disclose much of the information about it. What we know is it's built of fixed frequency qubits. The gates are parametric gates, which we'll discuss later on, basically applying the frequencies, which is a combination of resonance frequency of participating qubits. But in a way, this processor, if it really works properly, should be 10 to 22 times more powerful than Google chip, which already demonstrated its quantum supremacy. Of course, these processors, they have always limited coherence, and we'll talk later on what is actually the true value of these processors. If you make a processor of many thousands of qubits, but they all have short coherence time, then it's not useful for anything. You cannot do much, because the quantum kids, they forget their memory, forget where they started from, the state. So they need to sort of maintain the information about the initial state and all the manipulation by interaction with other qubits and external controls should be contained in the final state. And IBM actually came up with a proposal to characterize superconducting qubits processors by quantum volume. I'm not going to address this too deep. Maybe Alexey Fedorov or whoever told you about that before already did this, but roughly it's a product of the number of qubits, the number of gates which you can make to individual qubits without losing the coherence. And this quantum volume of IBM processors has been already claimed to be around 60. Now it's probably growing, which is not bad. So this is some ongoing development, which of course, for physicists interested in hardware and physics of these devices, like myself, are not so interesting. So this is really technology which now develops its own way, and this thing is going on. All right. Yeah, I think the time is up. Are there any questions?
Показывали на каком-то слайде был процессор, который был напечатан, я насколько поняла, на микроимне подложке, как производим с эфиром. Это тоже отдельное направление сейчас? И все-таки все как?
Ну, как-то в основном спустились на кремний, потому что эфир все довольно сложно его резать, дергать. Поэтому ну, и научились просто разные процессы. Сейчас, в принципе, времена когерентности на кремний ничуть не хуже, чем на сапфире. Казалось, нужно использовать очень такой до тупого простой процесс, погрузить всю схему в плавильную кислоту. И эта кислота убирает, если сделать это на короткое время, то она убирает всю гадость на поверхности. Единственное, если прекрасно, ничуть не хуже, чем на сапфире. Ну, как бы на сапфире, в принципе, используют в нем очень маленькие микроволновые потери в объеме. Поэтому, когда нужно использовать, например, кубиты для трехмерных резонансов, например, то, что делают в Ельском университете, большие белые резонансы, там они все делают на сапфире. Плюс сапфир прозрачный в видимой области, можно легко расположить кубит, не хочется пространства. На кремнии это все нужно делать одновременно. Ну, на кремнии используется другая процедура, называется флип-чип, где фактически используются кубитные чипы с резонаторами, и они лицом к лицу соединяются при помощи сверхпроводящих контактов. Вот. Но только обычно делается на кремнии, смотреть на это совмещение нужно в инфракрасном свете. Для этого существуют специальные машинки, которые смотрят на кремнию, прозрачный инфракрасный область, чтобы совместить два чипа вместе. Используется и то, и другое. Еще вопросы? Ладно, все голодные, давайте тогда на этом закончим.